Hello everyone, I'm Ningsheng from Shenzhen University, China. This is a joint work with our advisor Shubin and Professor Zhong Ming from Shenzhen University. Our work is about the scalability of blockchain, which is a hotspot in service network. In our paper, we proposed a novel blockchain framework with scalability, which uses sharding to improve the throughput. At the beginning, we will make a short introduction about blockchain. Blockchain is a solution to reach consistency in a distributed system without an authoritarian manager. When more than half servers in blockchain network agrees on all blocks, the system reaches consistency. All instructions captured in block must be voted by all pairs in accordance with the established rules. Notice that message can be lost, resent, or sent without order in propagation. Each block must contain a segment of data which declares block's location in the chain. Blockchain introduced hash function to ensure the order of blocks. Each block contains its precursor's digest and uses it as an anchor to ensure which block is the precursor. However, a dilemma called fork may emerge occasionally when one server received several legal blocks whose locations are same. In this figure, there are two forks in the chain. Fork makes disagreement among servers and damages the consistency of system. Therefore, blockchain introduced consensus mechanism to address fork. For example, Bitcoin requires every block's digest has at least the K prefix zeros. If the performance of message digest algorithm is good enough, then service can only search results by exhaustion. The more requirements for digest, the more difficulty and workload for generating blocks. However, restrict the generating block cannot completely eradicate fork. Blockchain still needs a rule to select out the only chain when fork appears. In Bitcoin, it rules that servers should receive the longest chain because the longest chain contains the most workload. If attacker wants to attempt the data stored in blockchain, he should not only generate blocks faster than others, but also rebuild all blocks who had been already write into the chain. Once the attacker computes at a slower rate than other honest nodes, his probability of success decreases exponentially with the growth of the chain. Blockchain makes it difficult to tamper with the data in the trustless environment. That's the value of the blockchain. Nevertheless, the existing blockchain solutions cannot match the traditional central service framework in latency, throughput, and scalability. In this paper, we concentrate on scalability of blockchain, which means the throughput of blockchain can be enhanced when the number of service nodes grows. In short, the methods to enhance the blockchain's performance concentrate on two directions. First direction is leader election. Leader can determine the global order of blocks, which can reduce the overhead, such as Bitcoin NG. In fact, the common consensus mechanism, like proof of work and proof of stake, used in the traditional blockchain are also forms of leader election. But leader election raises the centralization. The blockchains based on leader election have to frequently change the leader, which causes extra expenditure. Second direction is sharding, which means splitting service nodes into several committees. Sharding amortizes heavier communication tasks into two steps: generating blocks in the committees and synchronizing blocks among committees. In sharding, different committees in the system can independently select the disjoint requests from clients and package them into blocks. The biggest advantage of sharding is that different committees can generate blocks independently, which improves the throughput of the system. However, sharding also has three problems. First of all, we cannot guarantee that every committee is reliable because the percentage of malicious nodes may excel one half in some committees. So how to build committees becomes the difficulty. Another threat is how to achieve the agreement on secret blocks among servers. The last question is how to decide the number of committees. Before formally introducing our module, we will explain some terms and basic assumptions. Servers. Assuming that all service nodes have their own global unique identifiers and key pairs. Each node is either honest or malicious. Furthermore, all honest nodes do not go online forwardly, and when the honest one offline, he will eventually go online again as soon as possible. Clients and requests. Provided that all clients have their own global unique identifiers, public and private key pairs, every request will be encrypted and cannot be tampered. Network and communication. Assuming that the network is synchronized, which means the message may be disordered, retransmitted, and lost during transmission, but the content of the message will never be tampered. Each node can communicate directly with other nodes and clients. Committees. Every committee is either reliable or trustless. The proportion of malicious nodes in reliable committee is less than half. The first committee in our system, called Committee 0, which is reliable. Each committee initialized with C members. The number of members in committee known as half C and no more than double C. Next, we will explain notations in our paper. N means the number of service nodes in the service network. Nm means the number of malicious nodes. Nm1 means the number of malicious nodes in the trustless committee. Nm2 means the number of malicious nodes in the reliable committees. F means the proportion of malicious nodes in the system. K means the number of committees. C means the standard number of nodes in the committee. Ring means the topology inside the committee. TP means the expected time for executing proof of work. BX means the expected time for a broadcast to X nodes. S means the expected time for a unicast. In our solution, we introduce a tree structure to decide the sequence of groups. Also, the sequence of groups can decide the order of blocks. For reducing the message complexity, each committee should elect a leader in each period. We separate the system into two different modes, working state and splitting state. In working state, system will handle requests and generate blocks. In splitting state, system doesn't handle requests from clients but redistributes committees. When some committees reach a predetermined threshold and all committees have worked for long time enough, system will stop working and enter the splitting state briefly. Meantime, the original committee will be split into at most two sub-committees. After redistribution, each committee will return to working state. First, we will show how does system work in working state. In working state, the main task for service network is generating blocks. Just like any other sharding blockchain, generating blocks requires 3 steps. Generating block in a committee, synchronize blocks between committees, and re-elect the leader for each committee. In the first step, we exploit atomic broadcasts to build blocks in a committee. Because atomic broadcasts can eliminate the divergency and guarantee the consistency within cluster. In our solution, we introduce and reform the ring paxos to generate blocks inside the committees. Ring paxos requires nodes in the cluster forming a ring topology in each area. However, we didn't form ring topology in each area. Instead, this ring topology will be formed in redistributing committees. The advantage of using ring paxos is that every node needs only keep 2 heartbeat detection. Figure 1 shows the main workflow in generating blocks inside the committee. The committee leader chooses a set of requests according to its own state and packs them into a block. After that, leader will broadcast this block to all other committee members. Then leader can generate a special message called poll and send poll to its descendants nodes in the ring. One by one, Every node will add their opinions into poll and pass the poll along with the ring. When leader receiving the poll, it will broadcast the poll to all other members. If more than half members vote for block, then all members in these committees reckon this block is legal. All members in the committee will check and adjust their local state according to the poll and ensure the highly consistency inside this committee. However, leader may collapse during his work. There are several anomalies during generating block. Firstly, leader failed in packing or broadcasting block. Leader may collapse or refuse to do his duty deliberately and his committee had to create an empty block. When the number of nodes is less than half, this group cannot do their job and will perish. The rest nodes will rejoin the network and enter into other groups. Secondly, leader failed in passing poll. When leader failed in sending poll to his successor, the successor will rise as new leader and try to finish job. Thirdly, leader failed in broadcasting poll. The second last node in the ring will perform as the leader to complete the current round. At last, other non-leader nodes failed in sending poll. The third node will be skipped. If nodes still contain more than half the members, then this group still works. The second step called intra-committees synchronization. After generating block, leader will send his blocks and poll to other leaders. After synchronizing leader receiving blocks with their vital task is to elect leaders in next area. As we mentioned before, we introduce a tree structure the hash value and map committees to the nodes in their own group, so we can use unfair because the account leader can deliberately choose request and find a special combination. Apparently, malicious leader can deliberately make up from other committees are not committees or predictable. So we need to therefore we organize the blocks along with the order of groups and in the first round, hash tree. Leader will send and receive blocks and polls called seeds each other. Will decide who's the next interval. Every leader will broadcast his absence and try to fulfill the whole. We will look at in fact, they can require every leader broadcast the digest of reallocate the blocks and polls. Different from generating final gap, it will not in a hurry with the relevant leaders to resend blocks and file all clients don't know the gathering blocks and polls. Leaders will broadcast this message node finding his answer. The members each node will check and excuse request will reply to every block following the order from other nodes. Newborn server will rise the apparent to normalize during leader will set the measures and synchronization among special blocks derived from the community's synchronization. Where this will regard the block from most leader as the framework, and the block current period will synchronize with most two special blocks. However, the synchronization leader cannot take step is not who failed in joining the NVIDIA and synchronization, and they need to elect another person to handle is allocate synchronization and reliable leader failed in synchronization when attack will join maximize the avenue in this group doesn't though it will send a request to the next leader only as this information can only generate empty block called in this area. During next area of this committee must elect a leader, and the target synchronized can be blocks in the last period, and the current one reaches the peak when NM2 is 0. The limitation of the first factor in maximal value shows that the rate of trustless groups in our system will never reach double F when the proportion of malicious nodes in the system less than F. Therefore, the security of the system can be guaranteed with no more than half trustless groups, which requires F less than 1/4. Next, we will analyze the delay, message complexity, and the throughput among Bitcoin, Bitcoin NG, Elastic ICO, and our solution. Bitcoin generates only one block in each period after finishing proof of work, and therefore, the propagation delay in Bitcoin consists of proof of work and broadcast. In Bitcoin, each node needs broadcast its message to all peers, so the message complexity in Bitcoin increases linearly. In Bitcoin NG, the situation is slightly different from Bitcoin. After nodes finishing proof of work and broadcasting its answer, it could continuously output multi-blocks. Therefore, the delay in Bitcoin NG can be regarded as only one broadcast. Also, the message complexity is a linearity. In elastic ICO, the analysis is complicated. In each period, elastic ICO requires every node to finish proof of work and broadcast its answer to the dictionary committee to build committees. Building committees costs the same time as Bitcoin and linear message complexity. After building committees, elastic ICO explores practical Byzantine fault-tolerance algorithm in generating blocks within committees. In practical Byzantine fault-tolerance algorithm, leader broadcasts his block to other peers and then the cluster needs 2 round broadcasts. However, in this broadcast, every node must send their message to all other peers, and therefore it reaches quadratic message complexity. In normal practical Byzantine fault-tolerance algorithm, nodes need to send their decision to a learner, but in elastic ICO, the normal committees need to send their blocks to the dictionary committee, and the dictionary committee will recheck and reorder the request in these blocks. Also, dictionary committee using practical Byzantine fault-tolerance algorithm to make a decision. After making decision, every node in dictionary committee needs to broadcast blocks to all other groups. Finally, elastic ICO reaches the linear message complexity while power C are far less than n, and the total time cost can be expressed by expression below. In our solution, the overhead consists of 2 parts. Generating blocks within committees requires 2 blocks and C times the unicast. Synchronization requires 2 broadcasts among leaders and 1 times broadcast inside the committees. However, when leader broadcasts what he received among his group, the message contains not only 1 block but all blocks from other groups in current period. Therefore, our solution reaches the quadratic message complexity, and the total time cost can be expressed by expression below. Apart from analysis, we also designed simulation experiments. We simulated a decentralized distributed platform with 1,000 virtual nodes inside. For the sake of saving time, we introduced the event-driven mechanism instead of real-timer. Every node in our platform has the same resource allocation, and they can directly communicate with all other nodes, which means the consumption of bandwidth may be very huge. The benefit of equivalent allocation is that we can use a random number generator to decide the leader in each round without great energy consumption. In our simulation experiment, we used the number of blocks generated per second as a metric. In this figure, we notice that Bitcoin NG showed no scalability while elastic ICO and our solution did. Bitcoin NG doesn't optimize the network topology, and the propagation latency grows with the scale of network. From the figure, it is apparently that our solution excelled Bitcoin NG when the service node exceeded more than 250 nodes, while elastic ICO needs around 1,000 nodes. However, our curve becomes slow because more committees in the system, more time expenditure in the synchronization. Leaders will take more time to exchange blocks and broadcast more blocks to their peers. In conclusion, we introduced a novel sharding blockchain framework, which uses one kind of atomic broadcast protocol to generate blocks in the committee. Also, we used a tree structure to sort committees and their blocks, and when the members are too many in some committees, then committees will split into 2 subcommittees and increase throughput. To pair our solution with other framework, We designed simulation experiments and measured our solution with Bitcoin NG and Elastic ISO by the rate of generating blocks. However, there indeed exist some shortages in our system. Service nodes in our module need to store all clients and all other service global unique identifiers and a public key, which requires a great piece of memory. Memory may become the new bottleneck in our service. In future work, we will make further efforts to refine details in our framework and optimize it. If you had questions or suggestions, welcome sending our email. Thank you.